Okay, this set of videos discusses multivariate analysis techniques. It's very common techniques in biomedical engineering as well as other fields of engineering like geosciences, particularly in fields where you have multiple probes that are often measuring in a limited number of sources. So we'll first present the problem mathematically while we talk about an example as well. Basically, what happens in multivariate analysis is you're measuring multiple variables, and they're analyzed together, and a lot of times they're represented as a single vector that includes different variables. So, for example, here's our vector x that includes variables x sub m, x sub m1, x sub m2, and so on, where m is the number of variables and n is the number of observations. So this would not be uncommon, for example, to have multiple channels, which would be multiple variables, recording information as a function of time, which would be multiple observations. So we can draw that, or we can represent that in signal analysis as a matrix, where your rows consist of time points. Your columns consist of time points, and your rows consist of the different variables or channels. So in signal processing, these observations are time samples. In image processing, they're pixels. Multivariate data, as represented by this variable x, can also be thought of as residing in some m-dimensional space, where each dimension contains one set of observations. And the reason this is useful is that we can visualize things in 2 dimensions. So we can visualize operations on this multidimensional space in 2 dimensions so we get some deeper understanding, and then generalize that to more than 2 dimensions. Multivariate analysis also takes into account relationships between and within the multiple variables. So you can look at how a variable is developing as a function of observation. You can look at how another variable is developing as a function of observation time, and then you can compare the relationship between the 2 variables. Multivariate tools operate on all of the data. So, for example, covariance matrix includes information about the relationship between variables as well as about the variables themselves. A major concern in multivariate analysis is to find transformations of the data that will make the data set smaller or easier to understand. So there are a couple of questions that you ask here. The first question is, can the relevant information contained in a multidimensional variable be expressed using fewer variables or fewer dimensions? In other words, are any of the variables redundant? Secondly, can the data be transcribed to be more meaningful? If so, the more meaningful variables are described as the hidden or latent variables in the original data. So they're the latent variables. So here's a physiological example. We've been talking about the EEG, and as you know, EEGs tend to be measured as multi-channel systems. In fact, the data set that you were able to analyze had 60 channels. The reality is that there are probably some physiological signals, as represented by this circle on the left, which represents the brain. There are probably some physiological regions in the brain that are generating signals that are picked up by the EEG. And of course, this is a huge simplification, but we'll assume that of the perhaps millions of oscillating dipoles, even billions, within the brain, we'll assume that there are some collective phenomena that could be represented as a specific signal originating from a specific part of the brain that has some unique characteristic. So within the brain, we might have M locations or M sources that are emitting energy. But our measurement system might actually have N components. So we might have a 60-channel EEG system measuring, for example, 20 physiological signals. As a general rule, you want your number of measurement channels to be greater than your number of signals being measured, because this allows you to do something not unlike triangulation. So the measured variables are always a mixture of the x's. So for example, if I have a channel located, say, right here between x1 and x2, and that's my measurement channel, I'm picking up some of x1, I'm picking up some of x2, probably lesser amounts of x3 and 4, and even smaller amounts of 5 and so on. So proximity in this particular example has something to do with it, proximity of your sensor to your actual signal sources. So I have all of these sensors scattered around the brain, picking up information from these M sources as represented by X. And so what I really get as my output is I get these N channels of signals that consists of mixtures of M channels of actual sources or generators. And so what happens is, to get from sources to the signals that you measure, some physics process occurred. So if you're making, for example, an acoustical measurement, then your acoustic waves transmit through the room, they bounce off the walls, they're picked up by various microphones. So there's a physical model often that could be used to get from the sources or generators to the measurements or mixed signals. However, that process is often extremely complicated, and sometimes we don't even know what that process is. Now, if we know where all of the sources are located and what their intensities are and so on, we might be able to use that physics model to get and predict what measurement each channel might pick up. But in most biomedical problems and measurement problems, the opposite is actually the case. We have the measurement, and we have to solve the inverse problem to get back and figure out what the signals are. So the question is, not knowing much information about the signals, not even necessarily knowing a great deal of information about the physics, how do we take these measurements and get the signals back? And more specifically, if we do that, do the original signals or sources give us more information? Well, in this example, they obviously would, because we would get the specific locations of which parts of the brain were active. And they also, or we would at the very least get specific time domain signatures of active regions of the brain. And it might be that there are fewer regions of the brain active than there are measurements that are made. And reducing the data set is very significant, because basically this means that you don't have to deal with 60 channels, maybe you can deal with 10, which is an easier problem to solve if you're trying to do some sort of pattern recognition. Okay, so multivariate data transformations, what you really want to do is you want to figure out how to solve the inverse problem. Is there some way, given measurements, that you could get your original sources back? So we first have to think about it sort of in reverse. So we have these sources, x1 through xm, and then we have some matrix that's like a weighting matrix that was applied to x1 through xm, and then out of that we will get my's. Okay, so first of all, notice that we set the dimensionality to be the same. So we are initially making sort of an assumption that if we have m measurements, we have m sources. And the approach is going to be that basically, after we do this inverse transformation, some of those sources are going to be insignificant, and we're going to be able to tell how to figure out which ones those are. So initially, we have some variable, x1 through xm, some multiple variables. And there's some weighting function that's dependent upon the physics of the problem that then gives us the output. So this is basically a linear transformation. And it can either be written in a matrix form, or it can be written as a summation form. But these describe the transformation. So W is some matrix. Now, a linear transformation can be interpreted as like a rotation of the data set. So here's an example where we have a two-dimensional data set, x1 and x2. So two variables. And so what we're going to do is we're going to plot in a scatter plot every point its value in x1 and its value in x2. So if we have n observations, we'll have n of these dots, each containing an x1 part and an x2 part. And you can see that in this particular example, the data plot like this. Basically, what a linear transformation does is it takes this data set and rotates it. So you can see between the first graph, which is x1 versus x2, and the second graph, which is y1 versus y2, we've done a rotation of the data set. And the interesting thing there is that you can now see that almost all of the variation occurs in y1. And y2 doesn't have that much variation or that big a variance. So the variance along y1 is quite large. The variance along y2 is significantly smaller. So maybe the variance along y2, if it looks highly Gaussian, turns out to be just noise, and the real variable or the real variation is occurring in the dimension y1. So that's not necessarily obvious before rotation, but after rotation it becomes fairly obvious that we may have one variable that's basically noise and another variable that's actually the variable that we're interested in looking at. So rotating the data set in this way makes a lot of sense. Now, if that's the case, and this is very hypothetical, but hypothetically, let's suppose that after rotation, y2 does basically just represent noise. Then if what we're interested in is in understanding the problem and what's going on with our measurement, then we might be able to completely ignore the variable y2 and look only at the variable y1 if y2 indeed just represents noise. So in this two variable data set, this is of course a highly simplified way of looking at things because we often have multiple variables, but you can't visualize 60 channels. But effectively you're doing the same thing. You're plotting all the channels versus all the other channels in an m-dimensional space, and then you're using a rotation to basically minimize the number of variables that you have to deal with. So that's what principal component analysis basically is. So principal component analysis is a linear transformation that's used to transform one set of variables into another set of variables. And it's useful because then we can get information on the true dimensionality of a data set. So in the previous example, what looked like a two-dimensional data set was actually a one-dimensional data set with the second dimension taken up in noise. Principal component analysis will tell you if the data set can still be transformed, can be transformed into a fewer number of variables that still contain most of the essential information. And principal component analysis will implement that transformation. So it does this basically by rotating a data set or transforming a data set excuse me, until all the variables are uncorrelated. So that's kind of a geometrical interpretation. Remember, uncorrelated variables don't provide any information on one another, so they have no common information. But they're not necessarily independent. So examples that use only two variables as two variable data sets are a lot easier to plot and visualize, but basically this approach can be generalized to any number of variables. So here's an example of a two variable data set that's made from mixtures of two sine waves, each mixture containing different amplitudes of the sinusoids and different noise. And if you look, there's a high degree of correlation between signal x1 and signal x2. And if we now do a scatter plot before rotation, you can see that scatter plot appears right here. If we now rotate the scatter plot, you can now see that the two variables are no longer correlated. So what has happened between the previous example and this example is that principal component analysis has been applied and we have two new variables and they're both uncorrelated. However, notice that the new variables are still mixtures of the two original sources. So really, In this particular example, even though we have uncorrelated the variables, we don't have any information that's more meaningful than the original variables were. So this is an example of a data set that cannot be reduced. So in this case, you really do need two variables to represent these two sinusoids. In this case, basically what this is saying is the two measurement channels, that there are two measurement channels and two sources. So this is the case where principal component analysis breaks down. If the number of measurements and the number of sources are equal, and the sources are not interrelated, then you still can't necessarily minimize or understand the data better by applying principal component analysis, in which case you might need to use another technique. So I want you to contrast this case where we have this kind of scatter plot and these kind of variables yielded after principal component analysis. Contrast that with this case where we had a two variable data set that once rotation of the data occurred, we could see clearly that could be really reduced down to a one variable data set. So sometimes principal component analysis and a linear transformation can be very useful. Other times it's not necessarily so useful. Even though you manage to uncorrelate the data from, for example, this state, you can uncorrelate the data, you haven't really unmixed the signal. You now have still a new mixture. So in this case, a different technique would be used.